Hello there, and welcome to the Drowsy Inquirer. I'm so glad you found your way here tonight, because we're about to step into the most boundless idea the human mind has ever tried to hold. Tonight we're exploring infinity. Wherever you are right now, let this be your invitation to stop counting, stop measuring, stop drawing lines around things. Tonight we are going to a place where lines never end, where numbers never stop, and where the idea of the biggest simply does not exist. Infinity is not a number. It is not a place. It is not something you can hold or point to or reach. And yet it is everywhere. It hides between the numbers on a ruler. It spirals through the structure of a seashell. It sits quietly inside the endless digits of pi. And it has troubled, inspired, weighed and humbled the greatest thinkers in human history for over 2,000 years. Tonight, we will start with the simple act of counting and discover why it never has to stop. We will meet the mathematician who proved that some infinities are larger than others, and we will visit a hotel with infinite rooms that is completely full and yet can always welcome one more guest. We will walk through paradoxes that break our intuition, numbers that never repeat, and a universe that may stretch on forever without boundary or edge. Some of what you hear may surprise you. Some may feel like a puzzle you want to turn over slowly in your mind, and some may simply drift past, soft and unhurried, like numbers fading into the distance. If this kind of gentle wonder helps you relax or find your way to sleep, consider leaving a like or subscribing. Or it helps other curious minds find their way here too, one quiet night at a time. But for now, let your body settle, let your thoughts soften, and let's begin this slow, unhurried journey into the endless. You understood infinity before you could name it. Think back to being very young. At some point, perhaps with a friend, perhaps with a sibling, you played a game. Someone said a big number, the other said a bigger one, and then someone inevitably said the magic words, +1. Whatever number the other person said, you could always add one more. The game had no winner because it had no end. In that moment, without knowing the word, you discovered infinity, not as an abstract concept, not as a mathematical symbol, but as a feeling. The feeling that no matter how far you go, there is always further to go. No matter how high you count, there is always a next number. The staircase never stops. The road never ends. There is always one more. This intuition is remarkably powerful and remarkably correct. The natural numbers 1, 2, 3, 4, and so on do not have a largest member. There is no final number, no ceiling, no wall. You can count for your entire life and you will be no closer to the end than when you started, because there is no end to get closer to. This is perhaps the simplest definition of infinity. Not a destination, but a direction. Not a place you arrive at, but a journey that never finishes. And you knew it instinctively before you ever learned its name. Infinity is not a number, and it does not behave like one. It is tempting to think of infinity as the biggest possible number, a sort of ultimate quantity sitting at the far end of the number line. But infinity is not a number. It is a concept, and it follows rules that are entirely different from the rules of ordinary arithmetic. You cannot add 1 to infinity and get something bigger. Infinity plus 1 is still infinity. You cannot multiply infinity by 2 and get a larger result. Infinity times 2 is still infinity. And you absolutely cannot divide by 0 to get infinity, despite what your intuition might suggest. Division by 0 is undefined, a mathematical dead end, not a pathway to the infinite. These are not quirks or exceptions. They are fundamental features of what infinity is. Ordinary arithmetic works because numbers are finite, countable, and orderly. Infinity is none of these things. It does not sit on the number line. Why, it is not larger than all numbers in the way that 10 is larger than 9. It is a different kind of idea entirely. Mathematicians have developed careful, rigorous frameworks for working with infinity, from set theory to transfinite arithmetic. But even within those frameworks, infinity remains strange. It can be equal to a part of itself. It can contain other infinities within it, and it can produce results that feel impossible even when they are provably true. Infinity is not the biggest number. It is the idea that the biggest number cannot exist. The symbol for infinity has a surprisingly recent and uncertain origin. The figure 8 lying on its side, the lemniscate, is now universally recognized as the symbol for infinity. But it did not exist for most of the history of mathematical thought about the infinite. It was introduced in 1655 by John Wallis, an English mathematician, in his work Arithmetica Infinitorum. Wallis did not explain why he chose this particular shape, and scholars have debated it ever since. Some suggest it derives from the Roman numeral for 1000, which was sometimes written as CIO, a shape that could be stylized into a closed loop. Others propose a connection to the Greek letter omega, the last letter of the alphabet, symbolizing the end, or rather the absence of an end. Still others see a more poetic origin, a snake eating its own tail, the ancient Ouroboros, a symbol of eternal return found in cultures from Egypt to Norse mythology. Whatever its origin, the symbol has endured because it captures something essential about the concept it represents. It has no beginning and no end. You can trace your finger along it forever without lifting it from the surface. It loops back on itself endlessly, a visual metaphor for something that continues without termination. Before Wallis, mathematicians either avoided discussing infinity directly or used words and phrases to describe it. The symbol gave the concept a compact, portable form, something that could be written alongside finite numbers and manipulated within equations. It made infinity, for the first time, something you could put on paper. The ancient Greeks were both fascinated and frightened by infinity. The Greek mathematicians were among the first to think seriously about the infinite, and what they found disturbed them deeply. Infinity was not a source of wonder for the ancient Greeks. It was a source of anxiety. Aristotle, writing in the 4th century BCE, drew a distinction that would shape mathematical thought for 2,000 years. He divided infinity into two types. Potential infinity was the idea that a process could continue without end. You can always count one more number. You can always divide a line into smaller pieces. The process has no built-in stopping point. This kind of infinity, Aristotle accepted. It was safe because it was never completed. Actual infinity, on the other hand, was a completed totality, a set that contains infinitely many members all at once. The set of all natural numbers, for example, considered as a finished whole. This kind of infinity Aristotle rejected. He argued that the infinite could never exist as a completed entity. It was always in the process of becoming, never fully realized. This distinction held sway for centuries. Mathematicians avoided actual infinity, treating it as dangerous, paradoxical, and philosophically suspect. It was not until the 19th century that a single mathematician dared to challenge Aristotle's framework and declare that actual infinity was not only coherent, but richly structured. That mathematician's name was Georg Cantor, and his work would change mathematics forever. Zeno turned infinity into a weapon against motion itself. Around 450 BCE, the Greek philosopher Zeno of Elea devised a series of paradoxes designed to challenge the very idea of motion. The most famous of these is the paradox of Achilles and the tortoise. Imagine a race between the swift Achilles and a slow tortoise. The tortoise is given a head start. When the race begins, Achilles runs to the point where the tortoise started. But by the time he gets there, the tortoise has moved a little further ahead. Achilles runs to that new point, but again, the tortoise has moved on. Every time Achilles reaches the tortoise's last position, the tortoise has advanced slightly. The gap shrinks, but there are infinitely many gaps to close. How can Achilles ever catch up? In reality, of course, Achilles catches the tortoise easily. Anyone who has ever watched a fast runner overtake a slow one knows this. But Zeno's paradox is not about physical reality. It is about the mathematical structure hiding beneath it. If the distance must be divided into infinitely many intervals, and each interval requires some amount of time to traverse, then it seems like an infinite number of tasks must be completed, and infinity, by definition, has no end. For over 2,000 years, Zeno's paradox had no satisfying mathematical resolution. Philosophers argued about it. Mathematicians sidestepped it. And the question lingered like a quiet splinter in the foundations of logic. What does it mean to complete infinitely many steps? Calculus showed that infinity can be tamed. The resolution of Zeno's paradox came not from philosophy, but from mathematics, specifically from the development of calculus in the 17th century by Isaac Newton and Gottfried Wilhelm Leibniz, working independently. The key insight was the concept of a convergent series, an infinite sum that adds up to a finite value. Consider the series 1/2 plus 1, quarter plus 1, eighth plus 1, 16th, and so on, each term half the size of the previous one. There are infinitely many terms. The sum never stops growing, and yet it converges to exactly one, not approximately one, not close to one, exactly one. This was the answer to Zeno. Achilles does complete infinitely many steps, but the time required for each step shrinks so rapidly that the total time is finite. The infinite sequence of intervals, each one smaller than the last, adds up to a definite, finite duration. Achilles catches the tortoise in a perfectly measurable amount of time, and the infinity inside the process is not a barrier. It is simply a structure, a way of dividing a finite journey into infinitely many pieces, none of which prevent the journey from being completed. Calculus gave mathematicians a way to work with infinity safely. Infinite sums, infinite processes, infinitely small quantities, all of these could now be handled with precision and rigor. Infinity was not conquered. It was domesticated, turned from a philosophical threat into a practical tool, and with it, the door opened to modern physics, engineering, and every branch of science that depends on continuous change. Some infinite sums behave in ways that defy expectation. Not all infinite series converge so neatly. The harmonic series, which adds 1 plus 1 half plus 1/3 plus 1/4 plus 1/5 and so on, looks like it should converge. The terms get smaller and smaller, shrinking toward zero. Surely they must add up to some finite number. But they do not. The harmonic series diverges. It grows without bound, eventually exceeding any number you care to name. It does so extraordinarily slowly, so slowly that you could add up the first 10 billion terms and still be well under 30. But given enough terms, it surpasses 100, then 1,000, then 1 million, then any number you choose. It just takes an astronomically long time to get there. This is one of the many ways infinity surprises. Two series can look almost identical, one converging to a tidy sum and the other spiraling off to infinity, and the difference between them can be heartbreakingly subtle. The series 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared converges beautifully to pi squared over 6, a result discovered by Euler in 1735. But remove the squares and you get the harmonic series, which never settles down. Infinity does not care about our expectations. It is patient enough to wait and large enough to surprise, and it reveals its nature only to those willing to follow the numbers further than intuition alone can reach. One man dared to count the uncountable. In the late 19th century, a German mathematician named Georg Cantor did something that no one before him had attempted with full mathematical rigor. He asked a simple question with a revolutionary answer. Are all infinities the same size? The question itself seems strange. Infinity is infinity, you might think. How can one infinity be larger than another? But Cantor developed a way to compare infinite sets, not by counting their elements, which is impossible, but by trying to pair them up one to one. If every element of one set can be matched with exactly one element of another set, with nothing left over on either side, then the two sets are the same size. Cantor called this a bijection, a perfect one-to-one correspondence. And he discovered that some infinite sets can be placed in bijection with each other, while others cannot. The result was shocking. Not all infinities are the same. Some are genuinely, provably, rigorously larger than others. And the hierarchy of infinities does not stop. There is no largest infinity. For every infinity, there is a larger one waiting. Cantor's work was met with fierce opposition. Many of his contemporaries considered it nonsensical, even dangerous. But over the following decades, his ideas were vindicated, absorbed into the foundations of modern mathematics, and recognized as one of the most profound intellectual achievements in human history. He did not just study infinity, he mapped it. The even numbers are exactly as infinite as all the natural numbers. Here is a result that feels wrong, but is provably true. There are exactly as many even numbers as there are natural numbers. Not roughly as many, not half as many, exactly the same infinity. The proof is disarmingly simple. Line up the natural numbers in one column and the even numbers in another. Pair each natural number with the even number that is its double. 1 pairs with 2, 2 pairs with 4, 3 pairs with 6, 4 pairs with 8, and so on, forever. Every natural number gets exactly one even number. Every even number is claimed by exactly one natural number. Nothing is left over on either side. The two sets are in perfect one-to-one correspondence, which means by Cantor's definition, they are the same size. This is deeply counterintuitive. The even numbers are a proper subset of the natural numbers. You get them by throwing away all the odd numbers. It feels like you have removed half of the set, and yet the remaining set is just as large as the original. Nothing has been lost. This is one of the defining features of infinity. An infinite set can be the same size as one of its own parts. This is not true of any finite collection. If you remove half the chairs from a room, the room has fewer chairs. But if you remove half the numbers from an infinite set, the remaining set is just as infinite as before. Infinity is not diminished by subtraction. It simply rearranges itself and carries on. Even the fractions are no more numerous than the whole numbers. You might think that the fractions, the rational numbers, would form a larger infinity than the natural numbers. After all, between any two natural numbers, there are infinitely many fractions. Between 0 and 1 alone, there are 1/2, 1/3, 2/3, 1/4, 3/4, and infinitely more. The fractions seem denser, more numerous, more abundant, but Cantor proved that the rational numbers are countable. They can be placed in a one-to-one correspondence with the natural numbers. His method was ingenious. He arranged all positive fractions in a grid, with numerators along one axis and denominators along the other. Then he traced a zigzag path through the grid, counting each fraction as he encountered it, skipping duplicates. The result was a single, unbroken list that included every positive fraction exactly once. And because it was a list, it could be paired with the natural numbers. 1, 2, 3, 4, each one matched to a unique fraction. The set of all fractions, despite seeming infinitely richer than the set of whole numbers, is the same size. Both are countably infinite, belonging to the same level of infinity, designated by the symbol aleph null, the smallest infinity. This was a surprise, but the real shock was yet to come, because Cantor was about to show that not everything is countable. There is a level of infinity beyond Aleph Null, and it lives in a place you might not expect. The real numbers are a genuinely larger infinity. Between 0 and 1, there are infinitely many decimal numbers. Numbers like 0.5, 0.333 repeating, 0.7071, and so on. These include all the fractions, but also all the irrational numbers, the ones that cannot be expressed as a ratio of two integers. Numbers like the square root of 2, pi, and Euler's number e. Cantor proved that this set, the real numbers, us is uncountable. It cannot be placed in a one-to-one correspondence with the natural numbers. No matter how clever your listing, no matter how ingenious your scheme, you will always miss some real numbers. The proof is one of the most elegant arguments in all of mathematics, and it is called the diagonal argument. Suppose someone claims to have a complete list of all real numbers between 0 and 1, written as infinite decimal expansions. Cantor showed how to construct a new number that is guaranteed not to be on the list. You look at the first digit of the first number and choose a different digit, then the second digit of the second number and choose a different digit, then the third digit of the third number, and so on, moving diagonally down the list. And the resulting number differs from every number on the list in at least one decimal place. It cannot be the first number because its first digit is different. It cannot be the second number because its second digit is different, and so on for every number on the list. The new number is a real number between 0 and 1, but it is not on the list. This means the list was incomplete, and since the argument works for any possible list, no complete list can exist. The real numbers are uncountably infinite, a strictly larger infinity than the natural numbers. Some infinities are bigger than others. Cantor's diagonal proof is one of the most beautiful arguments in human thought. Let us sit with the diagonal argument a moment longer, because its beauty lies not in complexity, but in simplicity. Imagine a list, an infinite list. So each entry is an infinite decimal. The first entry might be 0.5, 0.00000, and so on. The second might be 0.3333333, repeating. The third might be 0.1415926, and so on. The list goes on forever, one entry for every natural number. Now construct a new number. Take the first digit of the first entry. If it is a 5, change it to a 6. Take the second digit of the second entry. If it is a 3, change it to a 4. Take the third digit of the third entry and change it. Continue forever, walking diagonally down and across the list. The number you have built is a perfectly valid decimal between 0 and 1, but it cannot be anywhere on the list. It disagrees with the first entry in the first digit. It disagrees with the second entry in the second digit. It disagrees with every entry in at least one place. It is new. It is real. And it was not counted. No matter how the original list was arranged, this trick always works. There is always a number hiding between the cracks. The real numbers cannot be tamed into a list. They overflow every attempt at enumeration. This is not a failure of imagination. It is a fundamental property of the continuum. The space between 0 and 1 is richer, denser, and more infinite than the endless march of whole numbers. Aleph Null is the smallest infinity, and it is the one you know best. Cantor gave the smallest infinity a name. He called it Aleph Null, written as the Hebrew letter Aleph with a subscript 0. It is the cardinality of the natural numbers, the counting numbers, the set that begins with 1 and never ends. Aleph Null is also the cardinality of the integers, including all negative numbers. It is the cardinality of the rational numbers, all possible fractions. It is the cardinality of the even numbers, the odd numbers, the prime numbers, and the perfect squares. All of these sets, despite looking very different, have the same size. They are all countably infinite. This does not mean they are small. Aleph Null is a staggeringly large infinity. It encompasses more elements than any finite number could describe, and yet it is the smallest possible infinity. There is nothing between finite and Aleph Null. Every infinite set is at least as large as Aleph Null. But as Cantor showed, Aleph Null is not the end. It is the beginning. The real numbers exceed it, and beyond the real numbers, there are larger infinities still. Aleph Null is the ground floor of an infinite skyscraper, and we have only just stepped inside. The continuum is a larger infinity that lives between 0 and 1. The cardinality of the real numbers, the set of all points on a number line, is called the cardinality of the continuum, denoted by the letter C, or sometimes by 2 raised to the power of Aleph Null. It is strictly larger than Aleph Null. The real numbers between 0 and 1 alone already exceed the entire set of natural numbers. To get a sense of how much larger the continuum is, consider this. The number of subsets of the natural numbers is equal to the continuum. Every possible way of choosing some natural numbers and leaving others out corresponds to a real number. And there are far more ways to do this than there are natural numbers to choose from. The continuum includes every rational number, every irrational number, every transcendental number like pi and e, and in every possible infinite decimal expansion. It is a smooth, gapless expanse of numbers, continuous and unbroken, filling in every crack between the countable points of the rational numbers. Between any two real numbers, no matter how close together, there are uncountably many others. The continuum is not just dense, it is impenetrably, overwhelmingly rich. It is a higher order of infinity, a level of endlessness that the countable numbers cannot reach, no matter how far they stretch. There is an infinity of infinities, and the hierarchy never stops. Cantor did not stop at 2 levels of infinity. He proved that for any infinite set, the set of all its subsets, called the power set, is strictly larger. This means that from Aleph Null, you can construct a larger infinity. And from that larger infinity, what you can construct a larger one still, and again, without end. The hierarchy of infinities is itself infinite. There is no largest infinity, no final level, no ceiling to the tower. For every infinity you can name, there is a bigger one waiting, constructed simply by taking all possible subsets of the previous one. This is called Cantor's theorem, and it applies to every set, finite or infinite. The power set of a 3-element set has 8 elements. The power set of a 10-element set has 1,024. And the power set of an infinite set has an infinity that is strictly, provably, inescapably larger. The result is a vast, endless hierarchy of infinities, each one containing more elements than the one before, each one unimaginably larger, each one just as real and just as rigorously defined as the counting numbers you learned as a child. Infinity is not a single, monolithic concept. It is a landscape, an endless ascending staircase, and Cantor was the first to see it. Cantor paid a personal price for seeing what others could not. Georg Cantor's ideas were revolutionary, and revolution is rarely welcomed quietly. Many of the most prominent mathematicians of his era rejected his work with unusual hostility. Leopold Kronecker, one of the most influential figures in German mathematics, called Cantor a corrupter of youth and actively worked to prevent him from obtaining a position at the University of Berlin. Henri Poincaré described Cantor's set theory as a disease from which mathematics would eventually recover. Even some who recognized the logical validity of Cantor's proofs were unsettled by their implications. The idea that some infinities are larger than others, that infinity is not a single, simple concept, but a vast, structured hierarchy, felt to many like an affront to mathematical intuition. Cantor struggled with severe depression throughout his life, and he spent several periods in sanatoriums. It is difficult to know how much of his mental suffering was caused by the professional isolation and hostility he faced, and how much had other origins. But the two were undeniably intertwined. He believed deeply in the truth and importance of his work, and the rejection he experienced was a source of profound pain. He died in 1918 in a sanatorium in Halle, Germany, but history vindicated him completely. David Hilbert, when one of the 20th century's greatest mathematicians, declared that no one shall expel us from the paradise that Cantor has created. Today, Cantor's set theory is one of the foundations of modern mathematics, taught in every university, used in every branch of the discipline. The man who counted the uncountable was right all along. Hilbert's hotel is always full and always has room. In 1924, the German mathematician David Hilbert proposed a thought experiment that has since become one of the most famous illustrations of the strange properties of infinity. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, 4, and so on, without end. And imagine that every room is occupied. The hotel is completely full. Now a new guest arrives and asks for a room. In any finite hotel, this would be impossible. But in Hilbert's hotel, the manager simply asks every current guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on, each guest shifting one room higher. Room 1 is now empty, and the new guest checks in. But it gets stranger. Suppose infinitely many new guests arrive, all at once. The manager asks each current guest to move to the room with double their current number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. Now all the odd-numbered rooms are empty, infinitely many of them, ready for infinitely many new guests. The hotel was full. It is still full. And yet it accommodated infinitely many newcomers without building a single new room. This is not a paradox. It is not a trick. It is a direct consequence of the properties of countable infinity. An infinite set can absorb another infinite set without growing. Infinity plus infinity is still infinity. The hotel never runs out of room because running out is something only finite things can do. You can remove infinity from infinity and still have infinity left. Imagine taking the set of all natural numbers, 1, 2, 3, 4, 5, and stretching it out to its endless horizon. Now remove every odd number. 1 is gone, 3 is gone, 5 is gone. Every single odd number removed. You have taken away infinitely many elements. What remains? The even numbers. 2, 4, 6, 8, 10, stretching on just as endlessly as before. The set you have left is just as infinite as the set you started with. You removed infinity from infinity and lost nothing. This is one of the most disorienting features of infinite sets. Subtraction does not work the way it does for finite quantities. If you remove 5 chairs from a room containing 10, you have 5 left. But if you remove infinitely many elements from an infinite set, the result depends entirely on which elements you removed and how. Remove all numbers greater than 1 million, and you are left with exactly 1 million, a finite set. Remove every other number, and you are left with an infinite set. Remove all but 1, and you have a single element. Infinity minus infinity is not a fixed quantity. It is undefined, capable of producing any result depending on context. This is why mathematicians treat infinity with such care. It is not a number you can subtract, divide, or manipulate with the casual confidence of everyday arithmetic. It requires its own rules, its own logic, and a willingness to abandon the intuitions that serve us so well in the finite world. The Banach-Tarski paradox makes the impossible mathematically true. In 1924, the mathematicians Stefan Banach and Alfred Tarski proved a theorem so counterintuitive that it sounds like a magic trick. Take a solid ball, like a sphere, using only rotations and translations without stretching, compressing, or adding any material. You can cut the ball into a finite number of pieces, rearrange them, and assemble two complete balls, each identical in size to the original. One ball becomes two. No new material is added. No stretching occurs. The total volume appears to double from nothing. It is mathematically proven, rigorously demonstrated, and absolutely impossible to perform in the physical world. And the trick lies in the nature of the pieces. They are not ordinary geometric shapes. They are infinitely complex, non-measurable sets. Collections of points so scattered and fragmented that they do not have a well-defined volume. They are the mathematical equivalent of dust so fine that it slips through every physical measurement. And when reassembled in the right configuration, they can fill a space larger than the one they came from. The Banach-Tarski paradox depends on the axiom of choice, a foundational principle in set theory that allows mathematicians to make infinitely many selections simultaneously from infinitely many sets. Without the axiom of choice, the theorem cannot be proved. With it, the impossible becomes inevitable. This result does not describe anything that can happen in the physical world. Atoms are discrete. Matter is finite. The pieces required by the theorem cannot be carved from real material. But in the abstract world of pure mathematics, where infinity and continuity reign, one ball can become two. It is a reminder that the mathematical universe is far stranger and far larger than the physical one. A shape with infinite surface area but finite volume. Imagine taking the curve described by the equation y equals 1 over x, starting from the point where x equals 1 and extending it to the right forever. Now rotate that curve around the x-axis, creating a three-dimensional shape that looks like a long, narrow horn, stretching infinitely far to the right, growing thinner and thinner, but never quite reaching zero. This shape is called Gabriel's horn, and it has a property that seems impossible. Its volume is finite. Specifically, the volume is exactly pi cubic units. You could fill it with a finite amount of paint, but its surface area is infinite. You could never paint the outside because there is always more surface, stretching endlessly along the narrowing horn. This creates a delicious paradox. You can fill the horn with paint, in which would coat the inside surface completely, but you cannot coat the outside surface because it is infinitely large. The paint that fills the interior, occupying a finite volume, somehow covers an infinite interior surface. But that same infinity of surface, viewed from the outside, would require infinite paint to coat. Gabriel's horn is a genuine mathematical object, rigorously defined and precisely measured. It exists at the boundary between the finite and the infinite, a shape that contains one within the other, a vessel that can be filled but never painted. It is one of the many places where infinity and geometry meet and produce something that feels like a riddle whispered by the universe itself. The length of a coastline depends on how closely you look. In 1967, the mathematician Benoit Mandelbrot posed a deceptively simple question. How long is the coast of Britain? The answer, it turns out, depends entirely on the length of the ruler you use. Measure the coastline with a ruler 100 kilometers long, and you get a certain length. The ruler skips over bays, inlets, and small peninsulas, tracing a rough, simplified outline. Now measure again with a ruler 10 kilometers long. The shorter ruler follows more of the coastline's curves, dipping into bays and around headlands that the longer ruler missed. The total length increases. Use a ruler 1 kilometer long, and the length increases again. 1 meter, and it increases further. 1 centimeter, and further still. As the ruler gets shorter, the measured length gets longer, because each reduction in scale reveals new detail, new crinkles, new irregularities that were invisible at the previous scale. In the mathematical limit, as the ruler approaches zero length, the coastline's measured length approaches infinity. The coastline is not a smooth curve with a definite length. It is a fractal, a shape whose complexity increases without bound as you examine it at finer and finer scales. This is called the coastline paradox, and it applies not just to Britain, but to every natural coastline, every mountain ridge, every riverbank. Nature does not draw smooth lines. It draws jagged, self-similar, endlessly detailed boundaries that resist simple measurement. The length of a coastline is not a fixed number. It is a question that infinity answers differently, depending on how closely you choose to look. Fractals make infinity visible. A fractal is a shape that exhibits self-similarity, meaning that it looks the same or similar at every scale. Zoom in on one part of a fractal and you see a smaller copy of the whole. Zoom in further and there is another copy and another and another, repeating endlessly no matter how deep you go. The most famous fractal is the Mandelbrot set, named after Benoit Mandelbrot, and generated by a remarkably simple formula applied repeatedly. The boundary of the Mandelbrot set is infinitely complex. No matter how far you zoom in, new structures emerge, spirals within spirals, tendrils branching into smaller tendrils, tiny copies of the whole set nestled within its own boundary. The detail never ends. And yet, the Mandelbrot set is generated by a formula that can be written in a single line. A finite rule applied infinitely many times, producing infinite complexity. This is one of the deepest themes in the study of infinity. Simplicity, iterated without end, creates boundless richness. Other fractals include the Sierpinski triangle, where a triangle is divided and subdivided until it becomes a lattice of holes containing no area at all, and the Koch snowflake, a shape with a finite area but an infinite perimeter. Each of these objects exists at the intersection of the finite and the infinite, contained within a bounded space but possessing detail that stretches on forever. Fractals are not just mathematical curiosities. They are windows into infinity, making the endless visible, the unbounded tangible, the infinite something you can almost hold in your hands. A monkey typing forever will eventually write Shakespeare. The infinite monkey theorem is one of the most vivid illustrations of what infinity means in the context of probability. It states that a monkey, pressing keys at random on a typewriter for an infinite amount of time, will almost surely type every possible text, including the complete works of William Shakespeare. The probability that a monkey will type the first word of Hamlet, whose, on any given attempt is astronomically small. The probability of typing the entire play is so small that it makes the word small seem generous. The number of possible combinations of keystrokes needed to produce Hamlet by chance is unimaginably vast. But infinity does not care about probability being small. It only cares that the probability is not zero. If there is any non-zero chance of an event occurring on a single trial, and then given infinitely many trials, the event will occur. Not might occur, will occur, with probability 1. This does not mean it would happen quickly. Even with 1 million monkeys typing 1 million characters per second, the expected time to produce a single page of Shakespeare would vastly exceed the age of the universe. The theorem is not about practical expectation. It is about the nature of infinity itself. Infinity turns the nearly impossible into the inevitable. It is patient beyond all measure. It does not rush. It does not give up. And given enough time, even the most improbable event becomes a certainty. This is the quiet power of the endless, a power that transforms chance into destiny, given only the luxury of forever. Pi never repeats and never ends. The number pi, the ratio of a circle's circumference to its diameter. It begins with 3.14159,265 and continues without end. Its decimal expansion is infinite. No matter how many digits you calculate, there are always more. As of recent records, over 100 trillion digits of pi have been computed, and the sequence shows no sign of repeating. Pi is an irrational number, meaning it cannot be expressed as a fraction of two integers. There is no ratio, no fraction, no finite decimal that exactly equals pi. It falls between the cracks of the rational numbers, occupying a place on the number line that no fraction can reach. Pi is also transcendental, a stronger property meaning it is not the solution to any polynomial equation with rational coefficients. This was proved by Ferdinand von Lindemann in 1882, and it settled one of the oldest problems in mathematics, the impossibility of squaring the circle with compass and straight edge alone. There is something quietly profound about a number that describes something as simple as a circle and yet contains within itself an infinite, non-repeating, unpredictable sequence of digits. A circle is the most symmetric, most harmonious shape in geometry, and yet the number at its heart is wild, untamed, and endless. The finite and the infinite, living side by side in the most basic shape in mathematics. Pi may contain every story ever written and every thought you have ever had. There is a conjecture, not yet proved but widely believed, that pi is a normal number. This means that in its infinite decimal expansion, every possible finite sequence of digits appears, and each appears with equal frequency. If pi is normal, and then somewhere in its digits is the string 1, 2, 3, 4, 5, 6, 7, 8, 9. Somewhere else is the string 999999999. Somewhere, encoded in some base, is the complete text of every book ever written, every song ever composed, every conversation ever spoken, and every thought you have ever had or ever will have, translated into numbers. Your birthday is in pi, your phone number is in pi, a digital photograph of your face, converted to a string of digits, is in pi. The exact sequence of digits representing the Declaration of Independence, a recipe for bread, or a love letter you have not yet written, all of them are there, buried somewhere in the endless stream. This does not mean pi is magical or omniscient. It is a consequence of infinity combined with randomness. Any infinite, non-repeating sequence that uses all digits fairly will inevitably contain every finite pattern. The information is not placed there by design. It emerges from the sheer, relentless accumulation of digits, one after another, forever. Pi is not a library, but if it is normal, then it contains, in a sense, every possible library. And it does so not through intention, but through the quiet, unstoppable arithmetic of the infinite. The discovery of irrational numbers shook the ancient world. The Pythagoreans, followers of the philosopher Pythagoras in the 5th century BCE, believed that all of reality could be expressed through ratios of whole numbers. Numbers were the fabric of the universe, and all numbers were rational, expressible as one integer divided by another. Harmony, geometry, music, everything could be reduced to the clean and orderly relationships between whole numbers. Then someone, tradition says a member named Hippasus, proved that the square root of 2 is irrational. It cannot be expressed as a fraction. No matter how you try, no ratio of integers will equal it exactly. The proof is elegant and devastating. Assume it can be expressed as a fraction in lowest terms, and you quickly arrive at a contradiction. The assumption must be false. The square root of 2 is not rational. According to legend, this discovery was so disturbing to the Pythagoreans that Hippasus was either expelled from the order or drowned at sea as punishment for revealing a truth that threatened the foundations of their worldview. Whether the legend is true or not, the mathematical reality is undeniable. The number line is not made entirely of fractions. There are gaps, uninfinitely many of them, filled by numbers that refuse to be expressed as ratios. The discovery of irrationals was the first hint that the number line is far richer and far stranger than anyone had imagined. There are far more irrational numbers than rational ones. This is one of those facts that seems impossible until you see the proof. The rational numbers, all possible fractions, are infinite. They are dense on the number line, meaning between any two real numbers, no matter how close, there is always a rational number. They seem to be everywhere. But the rational numbers are countable. They can be matched one-to-one with the natural numbers. They belong to the smallest infinity, Aleph null. The irrational numbers, on the other hand, are uncountable. They form a larger infinity, the same size as the continuum. This means that if you could somehow pick a real number at random, the probability of it being rational is zero. Not small, zero. Almost every point on the number line is irrational. The rational numbers are like stars in the night sky, bright and visible but scattered. The irrational numbers are like the dark sky itself, vast, continuous, and filling all the space between the stars. The points you can name, the fractions you can write down, are infinitely outnumbered by the points you cannot. This does not mean the rational numbers are unimportant. They are essential for measurement, for computation, for everyday life. But in the grand landscape of the number line, they are the exception, not the rule. The true fabric of the continuum is woven from irrationals, and it is infinitely richer than the tidy grid of fractions it contains. Euler's number appears wherever infinity meets growth. The number e, approximately 2.71828, is one of the most important constants in mathematics. Like pi, it is irrational and transcendental. Its decimal expansion never ends and never repeats. But while pi is the number of circles, e is the number of growth. It appears whenever a quantity grows continuously. Compound interest, if calculated with shorter and shorter compounding intervals, approaches a limit involving e. Population growth, radioactive decay, the cooling of a hot cup of tea, the spread of a rumor through a network, all of these follow curves shaped by e. The number e can be defined in many equivalent ways. One of the most elegant is as the sum of an infinite series. 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, and so on. Forever, each term is smaller than the last, and the sum converges to e, an infinite addition producing a finite, transcendent result. What makes e remarkable is its naturalness. It is not imposed on mathematics from outside. It emerges inevitably from the mathematics of continuous change. Wherever a process grows or decays in proportion to its current size, e appears. It is the fingerprint of infinity in the equations of the real world, a number born from endless repetition that shows up in the most fundamental descriptions of how things change. 5 fundamental constants meet in a single perfect equation. In the 18th century, the Swiss mathematician Leonhard Euler discovered a relationship so concise and so profound that it has been called the most beautiful equation in mathematics. It is written as a raised to the power of I times pi plus 1 equals 0. This single equation unites 5 of the most important numbers in mathematics. The number e, the base of natural growth, the imaginary unit I, the square root of -1, a number that does not exist on the real number line but is essential to complex analysis and quantum mechanics. The number pi, the ratio that defines every circle, the number 1, the building block of all counting, and 0, the absence that makes arithmetic possible. Each of these numbers was discovered in a different era, for a different purpose, in a different branch of mathematics. And yet they are connected, bound together by a relationship so simple it fits on a single line. There is no explanation for why it should be this elegant. There is no reason these 5 constants, not drawn from geometry, analysis, algebra, and arithmetic, should combine so neatly, and yet they do. Richard Feynman, upon first encountering the identity as a young student, called it the most remarkable formula in mathematics. Others have described it as a poem, a revelation, a glimpse of something deeper than mathematics itself. It is a moment where infinity, imaginary numbers, circles, unity, and nothingness hold hands, and the result is silence. Zero. Perfect stillness. The number line is infinitely dense, and you can never fill it. Between any two numbers on the number line, no matter how close together they are, there are infinitely many other numbers. Between 0 and 1, there are infinitely many. Between 0.5 and 0.51, there are infinitely many more. Between 0.5, 00001 and 0.50002, still infinitely many. In the process never bottoms out. There is no resolution at which the number line becomes granular or discrete. It is smooth all the way down. This property is called density, and both the rational and irrational numbers possess it independently. Between any two rationals, there is an irrational. Between any two irrationals, there is a rational. They are interwoven, interleaved, each set filling the gaps of the other, yet neither set completing the line alone. The real numbers taken together form a continuum, a seamless, gapless expanse that has no holes, no jumps, and no missing points. Every point on the line is accounted for. And yet between any two points, there are uncountably many others. The line is not just dense, it is unfathomably dense, rich beyond any finite description. When this infinite density means that you can never finish exploring the number line. No matter how closely you zoom in, there is always more structure, more numbers, more distinctions to be made. The number line is one of the simplest objects in mathematics, a straight line extending in both directions. And it contains within its elegant simplicity an infinity so deep that Cantor needed an entirely new mathematics to describe it. We do not know if the universe is infinite. This is one of the most fundamental unanswered questions in cosmology. Does the universe extend forever, stretching without limit in every direction? Or does it wrap back on itself, finite in total volume, but without any edge or boundary? The observable universe, the portion from which light has had time to reach us, is finite. It is a sphere roughly 93 billion light-years in diameter, centered on wherever you happen to be standing. But the observable universe is not the whole universe. It is simply the part we can see. Beyond the horizon of our observation, the universe may continue. It may continue for a very long way, or it may continue forever. Current measurements of the geometry of the universe, based on the cosmic microwave background and the distribution of galaxies, suggest that space is flat or very nearly flat. A perfectly flat universe in the simplest models is infinite in extent, but very nearly flat is not the same as perfectly flat. A universe with a very slight positive curvature could be enormous but finite, like the surface of an unimaginably large sphere. We would never notice the curvature at the scales we can observe, just as you cannot detect the curvature of the Earth by looking across a football field. The answer matters. An infinite universe has profoundly different implications than a finite one. In an infinite universe, every possible configuration of matter occurs somewhere. In a finite one, there are limits. The question of whether space goes on forever is not just a question about geometry. It is a question about the nature of possibility itself. If space is flat, it may extend without boundary forever. The geometry of the universe is determined by its total energy density, the combined contribution of all the matter, radiation, and dark energy it contains. If this density is exactly equal to a critical value, the universe is flat. If it is slightly above, the universe curves back on itself like a sphere. If slightly below, it curves outward like a saddle. Measurements from the Planck satellite, which map the cosmic microwave background with extraordinary precision, found that the universe's density is within 1% of the critical value. Space, as far as we can measure, is flat. In the standard cosmological model, a perfectly flat universe is infinite. It extends forever in every direction, with no edge, no wall, no boundary. Every point in an infinite flat universe looks the same as every other point. There is no center. There is no preferred location. The universe simply is, everywhere, endlessly. This does not mean we can observe it all. The speed of light and the finite age of the universe limit how far we can see. Beyond our cosmic horizon, space continues, filled with galaxies and stars and perhaps forms of matter we have never encountered. But we will never know for certain, because the light from those distant regions will never reach us. An infinite universe is not a conclusion. It is a possibility consistent with the data, supported by the simplest models, but not proven. The question remains open, and it may remain open forever, because proving that something is truly infinite requires seeing all of it, and that is something we can never do. The observable universe may be an infinitely small fraction of the whole. If the universe is indeed infinite, then the observable universe, vast as it is nothing. Not small, not a tiny fraction. Nothing in the mathematical sense. Any finite portion of an infinite whole has measure zero. It is like a single point on an infinite line, technically present but occupying no meaningful fraction of the total. And this is a humbling thought. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars. It spans 93 billion light years. It contains more atoms than you could count in 1 trillion lifetimes. And if the universe is infinite, all of this is an infinitesimally small patch, a single pixel in an image that extends forever in every direction. Beyond our horizon, there may be regions with different temperatures, different densities, perhaps even different configurations of matter. In an infinite universe, every arrangement that is not forbidden by the laws of physics will occur somewhere. Given enough space, the improbable becomes inevitable, not because of magic, but because of mathematics. Somewhere unimaginably far away, and the exact arrangement of atoms that makes up your body may be duplicated. Not approximately, exactly. Another you lying in another bed on another planet, listening to something, thinking something, being someone who is, in every physical sense, identical. This is not mysticism, it is arithmetic. In an infinite space, repetition is not just possible, it is unavoidable. Infinite space does not mean that everything imaginable exists. It is tempting to leap from the universe may be infinite to therefore everything exists somewhere. But this is not quite right. Infinity guarantees repetition within the rules, but it does not break the rules. Consider the even numbers. There are infinitely many of them. 2, 4, 6, 8, stretching on without end. But no matter how far you go, you will never find an odd number among them. The set is infinite, but it is constrained. It contains infinite variety within its rules and absolutely nothing outside them. The same logic applies to an infinite universe. If the laws of physics forbid a certain configuration of matter, then that configuration will not occur, no matter how much space is available. Infinity does not override the laws of nature. It operates within them, producing endless variation, but never violating the underlying structure. An infinite universe would contain every possible arrangement of atoms that is consistent with the laws of physics. But it would not contain impossible arrangements. No region where 2 + 2 = 5. No pocket where entropy runs backward indefinitely. No place where the speed of light is exceeded by a racing photon. The rules hold everywhere, forever. when an infinity explores every possibility they allow while respecting every boundary they impose. Singularities are where infinity appears in physics, and it usually means something is wrong. In general relativity, certain solutions to Einstein's field equations produce singularities, points where physical quantities like density or curvature become infinite. The center of a black hole is one such singularity. The initial state of the Big Bang is another. These infinities are not celebrated by physicists. They are regarded with suspicion. An infinite value in a physical equation usually means that the theory has been pushed beyond its domain of validity. It is not the universe that is infinite at a singularity. It is the theory that is breaking down. At the center of a black hole, general relativity predicts infinite density and zero volume. But most physicists believe this is an artifact of applying a classical theory to a regime where quantum effects dominate. A complete theory of quantum gravity, one that successfully merges general relativity with quantum mechanics, is expected to resolve the singularity, replacing the infinity with something finite, something strange, but something that makes sense. The same is true of the Big Bang singularity. The standard cosmological model, run backward in time, predicts that the universe was once compressed to a point of infinite density and temperature. But this prediction relies on classical physics. In the very earliest moments of the universe, we're almost certainly governed by quantum effects that our current theories cannot describe. Infinity in physics is not a feature of reality. It is a signpost. It points to the places where our understanding is incomplete, where new physics is needed, where the next great theory is waiting to be discovered. Physicists learn to subtract infinity from infinity and get the right answer. In the 1940s, physicists working on quantum electrodynamics, the quantum theory of how light and matter interact, ran into a serious problem. Their calculations kept producing infinite answers. The charge of the electron came out infinite. Its mass came out infinite. Every measurable quantity, when computed with full theoretical rigor, diverged to infinity. The theory was clearly getting something right because its predictions, when handled carefully, matched experiment with extraordinary precision. But the infinities were embarrassing and seemingly intractable. How could a theory that produced infinite answers be considered correct? The solution, developed independently by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, was a technique called renormalization. The idea in simplified form is to recognize that the infinities appear because the theory is trying to account for interactions at all possible energy scales, including infinitely high energies where the theory probably does not apply. By carefully isolating the infinite parts and absorbing them into redefined, measured values of quantities like mass and charge, the remaining finite predictions become extraordinarily accurate. The resulting theory, quantum electrodynamics, is the most precisely tested theory in the history of science. Its predictions match experimental results to more than 10 decimal places, and yet, at its heart, it relies on subtracting infinity from infinity to get a finite, correct answer. The physicist Paul Dirac was uncomfortable with this. He felt that a theory requiring such mathematical gymnastics could not be the final word. Others, like Feynman, accepted it pragmatically. It works. It gives the right answers. But no one fully understands why. Eternal inflation suggests that new universes are being born endlessly. Some versions of inflationary cosmology, the theory that the universe underwent a brief period of exponentially rapid expansion in its earliest moments, lead to a startling conclusion. Inflation may never stop everywhere. While it ends in some regions, allowing matter, galaxies, and stars to form, it continues in others, in endlessly spawning new regions of space. This is called eternal inflation, and it implies that the process of cosmic creation is not a one-time event, but an ongoing, eternal process. New pocket universes are constantly bubbling into existence, within an ever-expanding inflationary background. Each pocket universe may have different physical constants, different particle masses, different forces. The multiverse in this framework is not a fixed collection of parallel worlds. It is a continually growing, infinitely branching tree of realities. The total number of pocket universes in this scenario is infinite, and the process has no beginning that we can identify because the inflationary state may be past eternal as well. There is no first universe. There is no last. The chain of creation stretches forward and backward without end. Watch, this is speculative physics, not established fact. Eternal inflation is consistent with current observations, but it makes predictions that are extraordinarily difficult to test, precisely because the other pocket universes are beyond our cosmic horizon. We may never know for certain whether they exist, but if they do, then infinity is not just a mathematical abstraction. It is the actual structure of reality, an endless landscape of universes, each one a finite bubble in an infinite foam, each one a different expression of the possible. Nature writes infinity into ferns, rivers, and lungs. Fractals are not confined to the abstract world of mathematics. They are everywhere in nature, hidden in plain sight, woven into the shapes of living things and the patterns of the physical world. Look at an RLTO2, a fern. Each frond is lined with smaller leaflets. Each leaflet is lined with even smaller leaflets. And each of those, if you look closely enough, echoes the shape of the whole frond. The pattern repeats at smaller and smaller scales, a natural fractal written in chlorophyll and cellulose. River networks follow the same logic. A great river is fed by tributaries. Each tributary is fed by smaller streams. Each stream is fed by rivulets. The branching pattern at the largest scale looks remarkably similar to the branching pattern at the smallest. The river does not plan this. It emerges naturally from the physics of flowing water, finding the most efficient path downhill. Lightning bolts branch in fractal patterns as electrical discharge seeks the path of least resistance through the atmosphere. Mountain ridges, when viewed from above, show self-similar jaggedness at every scale. The distribution of galaxies across the universe, at certain scales, exhibits fractal-like clustering. Nature does not draw smooth lines. It draws fractal ones, rough, branching, self-similar shapes that contain more detail the closer you look. And in this roughness, this endless layering of pattern within pattern, infinity finds a home in the physical world. Not as a completed totality, but as a tendency, a direction, a whisper of the endless within the finite. Your lungs contain a surface area that approaches the infinite. Every breath you take depends on a piece of biological engineering so elegant that it borders on the mathematical. Your lungs are not simple balloons. They are fractal trees, branching and rebranching over 23 levels of division, from the trachea down to the tiniest bronchioles, each one splitting into two smaller passages. At the very tips of this branching network are roughly 300 million tiny air sacs called alveoli. These grape-like clusters are where oxygen passes from the air into your bloodstream and carbon dioxide passes out. Each alveolus is impossibly thin-walled, surrounded by a mesh of capillaries so fine that red blood cells must pass through them in single file. The total surface area of all your alveoli, if spread flat, we would cover approximately 70 square meters, roughly the area of half a tennis court. All of this is folded, compressed, and packed into your chest cavity, a space not much larger than two fists held side by side. This is the power of fractal geometry applied by evolution. By branching and rebranching at ever smaller scales, your lungs create an enormous surface area within a compact volume. It is the same principle that makes coastlines long and fern fronds detailed. Repeated subdivision, approaching but never quite reaching the infinite, producing a surface far larger than the space that contains it. Every breath is a quiet collaboration between your body and a geometry that flirts with infinity. A finite chest containing an almost infinite surface, exchanging gases with the efficiency that only fractal architecture can provide. Your trees branch according to patterns that mathematics can describe. A tree is one of the most visible fractals in the natural world. Stand beneath an oak in winter when the leaves are gone and the branching structure is fully visible, and you are looking at a self-similar pattern that repeats from trunk to twig. The trunk splits into major branches. Each major branch splits into smaller branches. Each smaller branch splits into twigs, and each twig, if conditions allow, would split further still. The angle of branching, the ratio of parent to child branch thickness, and the overall shape of the canopy all follow patterns that can be modeled with fractal mathematics. Leonardo da Vinci observed in the 15th century that the total cross-sectional area of all the branches at any given height of a tree is roughly equal to the cross-sectional area of the trunk. This rule, now called da Vinci's rule, has been confirmed by modern studies and is thought to be related to the hydraulic efficiency of water transport within the tree. The fractal dimension of a tree's branching pattern, a measure of how thoroughly it fills space, varies by species. Some trees, like elms, have a high fractal dimension, filling their canopy densely. Others, like birches, have a lower dimension, creating a lighter, more open structure. A tree does not know what a fractal is. It has no concept of self-similarity or scaling laws. It simply grows, following the chemical and physical signals encoded in its genes and shaped by its environment. And in doing so, it produces a structure that mirrors the infinite repetition of mathematical fractals, a living testament to the patterns that emerge when simple rules are applied again and again. Every snowflake carries infinite possibility in finite form. When a water molecule freezes, it bonds with its neighbors at angles determined by the geometry of the hydrogen bonds, producing a hexagonal lattice. This hexagonal symmetry is the foundation of every snowflake structure, from the simplest plate to the most elaborate stellar dendrite. As a snowflake falls through the atmosphere, it passes through regions of varying temperature and humidity. These conditions determine how the crystal grows, whether it branches or remains compact, and whether it develops broad plates or fine needles. Because the conditions change continuously, and because all 6 arms of the snowflake experience roughly the same conditions simultaneously, each arm develops the same pattern, producing the characteristic 6-fold symmetry. But the exact path of each snowflake through the atmosphere is unique. No 2 snowflakes pass through exactly the same sequence of temperatures and humidities. The result is that while all snowflakes share the same hexagonal symmetry, the details of their branching patterns are different. Each snowflake is a unique expression of the infinite possible variations within a fixed set of rules. The number of possible snowflake shapes is, for all practical purposes, infinite. The water molecules can arrange themselves in an almost limitless number of configurations, while each one valid, each one consistent with the underlying physics, each one different from every other. A snowflake is a finite object, small enough to rest on the tip of your finger, containing within it a single answer to an infinitely large question. The Fibonacci sequence spirals through the living world. In the year 1202, an Italian mathematician named Leonardo of Pisa, better known as Fibonacci, introduced a sequence of numbers to the Western world that would turn out to be embedded in the fabric of nature itself. The sequence begins simply: 1, 1, 2, 3, 5, 8, 13, 21, 34. Each number is the sum of the 2 before it. The rule is finite. The sequence is infinite. What makes the Fibonacci sequence remarkable is not its mathematical properties, though those are elegant, but its persistent appearance in the natural world. The number of petals on a flower is often a Fibonacci number. Lilies have 3, buttercups have 5, delphiniums have 8, marigolds have 13, daisies often have 21, 34, 55, or 89. The spirals in a sunflower head follow Fibonacci numbers. If you count the spirals curving to the left, you might find 34. Curving to the right, 55. These are consecutive Fibonacci numbers. The same pattern appears in pine cones, pineapples, and the arrangement of leaves around a stem. The reason is not mystical, it is geometrical. The Fibonacci pattern emerges naturally when a growing structure, like a plant tip, adds new elements at a constant angle relative to the previous one. The angle that produces the most efficient packing, the one that avoids overlapping and maximizes exposure to light, happens to be related to the golden ratio, which itself is intimately connected to the Fibonacci sequence. A simple rule, applied repeatedly, producing a pattern that spans the living world. The infinite sequence in the finite flower, connected by a thread of mathematics that neither knows it is following. The golden ratio emerges from the infinite. As the Fibonacci sequence progresses, something beautiful happens. The ratio between consecutive terms begins to converge. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3 is 1.66 repeating. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. The ratios oscillate, narrowing in on a single value. That value is the golden ratio, denoted by the Greek letter phi, approximately 1.6180, 339,887, and continuing forever without repeating. It is irrational. Its decimal expansion never ends and never settles into a pattern. And yet it arises naturally, inevitably, from the simplest of recursive rules. The golden ratio has a unique mathematical property. It is the only number that is exactly 1 more than its own reciprocal. Phi equals 1 plus 1 over phi. This self-referential definition creates a kind of infinite loop, a number defined in terms of itself, echoing the recursive nature of the sequence that generates it. Artists, architects, and designers have been drawn to the golden ratio for centuries, often claiming that it produces the most aesthetically pleasing proportions. Whether this is genuinely rooted in human perception or is partly a cultural myth is debated, but its mathematical beauty is beyond question. A finite number, born from an infinite process, appearing unbidden in flowers, spirals, and the quiet geometry of growth. Infinity has troubled theologians for as long as it has troubled mathematicians. Long before Cantor formalized the mathematics of infinity, the concept occupied a central and often uncomfortable place in theological thought. If God is infinite, what does that mean? Can the human mind, which is finite, comprehend the infinite? And is it appropriate to try? In the medieval Christian tradition, infinity was often reserved exclusively as an attribute of God. God alone was infinite in power, knowledge, and duration. Creation, by contrast, was finite. To claim that anything in the created world was truly infinite was, for some thinkers, to trespass on the divine. Thomas Aquinas, writing in the 13th century, argued that actual infinity could not exist in the physical world, but that God's infinity was of a different, higher kind, not a mathematical quantity, but a fullness of being, an absence of limitation. For Aquinas, infinity was not about numbers, it was about perfection. Cantor himself was deeply religious, and he saw no conflict between his mathematics and his faith. He believed that the transfinite numbers he discovered were glimpses of the divine mind, reflections of God's infinite nature expressed in mathematical form. He even corresponded with Pope Leo XIII about the relationship between his work and Catholic theology, and the tension between the mathematical and the mystical, between infinity as a calculable quantity and infinity as a spiritual mystery, has never fully resolved. It lives on in the quiet unease that many people feel when confronted with the idea that the endless can be studied, measured, and compared. Infinity resists domestication, even as mathematics refines its tools for doing exactly that. Does infinity actually exist in the physical world? This is a question that sits at the boundary of physics and philosophy, and it has no settled answer. Mathematics freely uses infinity in its constructions. Infinite sets, infinite sums, infinite dimensional spaces. These are everyday tools in the mathematician's workshop. But whether anything in the physical universe is truly infinite remains an open question. Quantum mechanics introduces the Planck length, approximately 10 to the power of negative 35 meters, and the Planck time, approximately 10 to the power of negative 43 seconds. These are often described as the smallest meaningful units of space and time, below which the known laws of physics cease to make sense. If space and time are genuinely quantized, divided into indivisible units like pixels in a digital image, then the physical world may not contain actual infinity at all. In a discrete universe, there would be no infinite divisibility. The number of possible configurations of matter in a finite region would be finite, though staggeringly large. The continuum, that smooth, gapless number line that Cantor explored, might be a mathematical idealization with no direct counterpart in physical reality. On the other hand, some physicists argue that quantization at the Planck scale does not necessarily mean that space is discrete. The mathematics of quantum gravity is far from settled, and it is possible that continuous, infinitely divisible spacetime is the correct description even at the smallest scales. The question remains beautifully open. Is infinity a feature of the universe, or only of the mathematics we use to describe it? Does the endless actually exist, or is it a human invention, a tool so powerful that we mistake it for reality? The continuum hypothesis is a question mathematics cannot answer. Among the many strange consequences of Cantor's work, one stands out as uniquely haunting. Cantor proved that the real numbers are a larger infinity than the natural numbers. He proved that there is a hierarchy of infinities, yet each one strictly larger than the last. But he could not determine whether there is an intermediate infinity, one larger than the natural numbers, but smaller than the real numbers. This question is called the continuum hypothesis. Is there a set whose cardinality is strictly between Aleph null and the continuum? Cantor believed the answer was no, that there is no intermediate infinity, but he could not prove it. In 1940, Kurt Gödel showed that the continuum hypothesis is consistent with the standard axioms of set theory. You cannot disprove it. In 1963, Paul Cohen showed that the negation of the continuum hypothesis is also consistent. You cannot prove it either. The continuum hypothesis is independent of the axioms. It is neither true nor false within the standard framework of mathematics. It is undecidable at a question that the rules of the game are insufficient to answer. You can adopt it as an axiom or reject it, and either choice leads to a perfectly valid, perfectly consistent version of mathematics. This is one of the most profound discoveries in the history of human thought. There are questions about infinity that are not merely unknown, but unknowable within our current foundations. The mathematical universe has limits, not of size, but of decidability. And some of the deepest questions about the infinite may remain forever beyond the reach of proof. Mathematics itself has limits, and Gödel found them. In 1931, a young Austrian logician named Kurt Gödel published two theorems that shook the foundations of mathematics. His incompleteness theorem showed that any consistent mathematical system powerful enough to describe basic arithmetic must contain true statements that cannot be proved within the system. The first theorem says that there are true statements about numbers that no finite proof, following the rules of the system, can establish. These are not obscure artificial constructions. They are genuine mathematical truths, lurking within the system, visible in some sense but unreachable by its methods. The second theorem goes further. It says that no such system can prove its own consistency. A mathematical framework cannot guarantee, from within, that it will never produce a contradiction. To prove consistency, you must step outside the system and appeal to a stronger one, which then faces its own incompleteness. Gödel's theorems do not mean that mathematics is broken or unreliable. They mean that mathematics is inexhaustible. No finite set of axioms can capture all mathematical truth. There will always be more to discover, more to prove, more that lies beyond the current horizon. Mathematics, like infinity itself, cannot be completed. It is a humbling and beautiful result. The human mind, using the tools of logic and proof, can reach extraordinary heights, but it can never reach them all. There will always be truths that are true but unprovable, questions that are meaningful but unanswerable, and depths that are real but unreachable. Even infinity has its own form of incompleteness. Borges imagined a library that contains every possible book. In 1941, the Argentine writer Jorge Luis Borges published a short story called The Library of Babel. In it, he imagined a library of infinite extent, composed of identical hexagonal rooms, each lined with bookshelves. Every book in the library is exactly 410 pages long, and every possible combination of 25 characters, letters, spaces, commas, and periods fills those pages. The result is a library that contains every book that could ever be written. Somewhere in its shelves is a perfect biography of your life, accurate in every detail. Somewhere else is the same biography with one word changed. Somewhere is the cure for every disease, the answer to every question, the resolution of every mystery. And surrounding each of these meaningful books are billions upon billions of volumes filled with nothing but random gibberish. The library is a parable about infinity and meaning. In an infinite collection, everything that is possible is present, but finding what matters within the vast ocean of noise is nearly impossible. The librarians of Babel search for meaningful texts and go mad in the attempt, overwhelmed by the sheer volume of nonsense surrounding every island of meaning. Borges did not use the language of set theory or transfinite arithmetic, but his library is, in its own way, a meditation on the same themes Cantor explored. Infinity contains everything, but containment is not the same as accessibility. The infinite library has every answer, but without a way to find them, the answers are indistinguishable from noise. Infinity is not about size, it is about possibility. After everything we have explored tonight, it is worth pausing to consider what infinity really means. Not as a number, not as a measurement, not as a quantity that can be compared, subtracted, or contained, but as an idea. Infinity means that there is always more numbers, more space, more detail, more depth. No matter how far you go, no matter how closely you look, no matter how much you count, there is always further to go. The process never finishes, the question never settles, the road never ends. This is not a limitation, it is a liberation. It means that mathematics will never be exhausted, that science will never run out of questions, that the universe, if it is infinite, will never stop offering new mysteries, and that your own capacity for wonder, for curiosity, for asking one more question, is itself a kind of infinity. Infinity is not frightening, it is generous. It says that the story does not end, that the next chapter is always waiting, that no matter how much you have learned, there is something you have not yet imagined. It is the mathematical name for the feeling you had as a child, lying in the grass, looking up at the sky, and realizing that it just keeps going. A grain of sand contains a kind of infinity. The poet William Blake once wrote, "To see a world in a grain of sand and a heaven in a wildflower, hold infinity in the palm of your hand and eternity in an hour." It is a line of poetry, not mathematics, but it captures something that mathematics confirms. A single grain of sand contains roughly 50 quintillion atoms. Each of those atoms is made of protons, neutrons, and electrons. Each proton and neutron is made of quarks. Each quark interacts with gluons, and at each level the physics becomes richer, deeper, more detailed. The grain of sand in your hand was once part of a larger rock, which was once part of a mountain, which was built from tectonic forces over millions of years, from minerals forged in the hearts of ancient stars. The atoms in that grain are billions of years old. They have been part of oceans, atmospheres, living things, and now briefly, a grain of sand resting on a beach. A finite object, small enough to sit on your fingertip, containing a history that stretches back to the origin of the universe, and a structure that extends down to the quantum scale. Not infinite in the mathematical sense, but infinite in the sense that matters most to a quiet mind on a sleepy night. An endlessly deep, endlessly connected, endlessly worthy of wonder. Between any two heartbeats, there is infinite divisibility. Your heart beats roughly once per second, a steady rhythm that you rarely notice unless you stop and listen. Between one beat and the next, about a second passes, a finite interval, measurable, ordinary. But mathematics tells us that this interval, like all intervals on the real number line, can be divided infinitely. The first half second, the first quarter, the first eighth, the first 16th. Each division produces a new, smaller interval, and each of those can be divided again. There is no smallest piece. The process never reaches a final, indivisible moment. Whether physical time is truly continuous, infinitely divisible down to the Planck scale and beyond, is an open question. But in the mathematical model we use to describe time, the interval between two heartbeats contains uncountably many instants. More instants than there are natural numbers. More instants than you could ever count, even with infinite time. You are not living from one heartbeat to the next across a handful of moments. You are traveling through an infinity of instants, each one as real as any other in the mathematical continuum. Your experience smooths them into a single, seamless flow. But beneath that flow, the mathematics of the infinite is at work, dividing and subdividing endlessly between every beat of your heart. Your mind contains a personal infinity. The human brain has roughly 86 billion neurons. Each neuron connects to thousands of others, creating a network of approximately 100 trillion synaptic connections. And the number of possible patterns of activation across this network is staggeringly large, far exceeding the number of atoms in the observable universe. In a strict mathematical sense, the number of brain states is finite. There are a fixed number of neurons, a fixed number of synapses, a finite number of possible configurations. But the number is so large that it is, for all practical purposes, inexhaustible. You could think a new thought every second for the rest of your life and never come close to exhausting the possibilities. Every memory you hold, every dream you have dreamed, every idea you have considered and discarded, every fleeting image that passed through your mind and vanished, all of these are patterns in this network, and the space of patterns you have not yet explored is incomprehensibly vast. Your brain is not infinite, but its capacity for novelty, for surprise, for the creation of new thoughts from old components, approaches infinity in the way that a fractal coastline approaches infinite length. It is bounded but inexhaustible. finite but endlessly rich. And it is working right now, even as you listen, even as you drift, producing thoughts that have never existed before and may never exist again. Sleep is a nightly encounter with the boundless. Every night, as you close your eyes and let go of the day, something remarkable happens. Your conscious mind, that restless narrator that divides the world into categories and counts and measures, begins to fade. The boundaries that define your waking life, the edges between self and world, between here and there, between now and then, start to dissolve. In sleep, time behaves strangely. Our hours can pass in what feels like moments. A dream that seems to last an afternoon may occupy only a few minutes of REM sleep. The strict, measured time of clocks gives way to something more fluid, more elastic, more like the mathematical continuum than the discrete tick of a second hand. Dreams are their own kind of infinity. The space of possible dreams is unbounded. Every scenario, every landscape, every impossible combination of memory and imagination is available. In dreams, you can fly, you can breathe underwater, you can meet people who do not exist, and visit places that have no coordinates. The constraints of waking life are lifted, and the mind roams freely through a space that has no walls. Sleep is not infinity, but it is the closest your consciousness comes to the infinite each day. A dissolution of limits, an expansion into the unmeasured, a small death and a small rebirth, repeated nightly, as natural as breathing and as mysterious as anything in mathematics. Infinity does not need you to understand it. It simply continues. Here's the most comforting thing about infinity. It does not require your attention. It does not need your comprehension. It does not wait for you to count to it, reach it, or understand it. It simply is. Right now, as you lie still, the digits of pi are continuing. Not literally, of course, pi is not a machine running somewhere, but in the mathematical sense, its digits are already determined, already fixed, already stretching out beyond any computation that has ever been performed or ever will be. The 100 trillionth digit is as real as the first. It simply has not been calculated yet. The natural numbers continue. After every number you have ever thought of, there is another. After every large number anyone has ever named, there is a larger one. The sequence does not pause, it does not rest. It simply extends endlessly without fatigue or hesitation. And if the universe is infinite, then right now, while you are falling asleep, it extends beyond the edge of your observable horizon, beyond the last galaxy whose light will ever reach you, into regions you cannot see and cannot imagine, stretching on and on and on. You do not need to follow it. You do not need to understand it. You do not need to hold it all in your mind. Infinity is not a task. It is a presence. It is the quiet assurance that there is always more, that the story does not end, that the last word has not been spoken and never will be. And that is enough. And now let the idea of infinity gently soften into quiet wonder. We have traveled far tonight. We began with a child's game, the simple realization that you can always add one more, and we followed that thread into territories that no child could imagine. We met Georg Cantor, who proved that some infinities are larger than others, and paid a personal price for seeing what others could not. We visited Hilbert's Hotel, where fullness and vacancy coexist without contradiction, and we walked through paradoxes that break our intuition while obeying the strictest logic. We watch pi's digits stretch on forever without repeating, and we imagine that somewhere in those digits, every story ever told is waiting to be found. We saw fractals in ferns and coastlines, heard the Fibonacci sequence in the spirals of sunflowers, and felt the golden ratio emerge from the infinite like a pearl forming in an oyster. We asked whether the universe itself is infinite and found that the question may never be answered. We learn that mathematics has limits, that some truths cannot be proved, and that the continuum hypothesis floats in a space between truth and falsehood that no axiom can resolve. Through it all, a single quiet truth kept returning. Infinity is not a number to be reached. It is a direction to be traveled. It is the assurance that there is always more, always deeper, always further. It is the mathematical name for the feeling that the world is richer than you can possibly imagine. You carry a piece of infinity within you, not literally, but in the way that matters. Your capacity for thought, for wonder, for dreaming, for asking one more question. And this is your personal infinity, bounded by biology but inexhaustible in practice. You will never think every thought your brain can produce. You will never dream every dream. You will never reach the end of your own curiosity because there is no end to reach. Tonight, as you rest, the numbers continue. Pi does not pause. The Fibonacci sequence does not sleep. The hierarchy of infinity stands unchanged, patient and permanent, untroubled by the passage of time. And somewhere, if the universe is truly infinite, there are stars being born right now that no telescope will ever see, in regions of space that no light from here will ever reach. You do not need to hold all of this. You do not need to understand it. You only need to let it be, the way you let the darkness be, the way you let sleep arrive without forcing it. Infinity is not a burden, it is a lullaby. The gentlest possible assurance that no matter what, there is always more. So let your eyes stay closed. Let your thoughts grow soft at the edges, like numbers fading into the distance. Let the infinite stretch out in every direction, quiet and unhurried, asking nothing of you except that you rest. Sleep well. Infinity will be here when you return. It always is. It always will be. Good night.